All right, in this section, we're looking at section 8.5, which is on annuities, methods of savings, and investments. The compound interest formula A equals P times 1 plus R to the T gives the future value A after T years when a fixed amount of money is deposited into an account that pays an annual interest rate R compounded once a year. So this particular formula, remember, is for N equals 1, which is for annual compounding. However, money is often invented in small amounts at periodic intervals. So for example, to save for retirement, you might decide to place $1,000 into an individual retirement account, also called an IRA, at the end of each year until you retire. Or more commonly, most of us, if we have a retirement account through our employer, we deposit some money each paycheck. So this could be weekly or biweekly. So usually we're not making like a one-time lump sum deposit. We're usually making small deposits over time to hopefully allow that account to grow. An annuity is a sequence of equal payments made at equal time periods. An IRA is one example of an annuity. And actually, I will say that there are IRAs as well that are not annuities. So the term annuity is being used here very generally to mean any sort of account that would have a series of equal payments made at equal time periods. But when you do retirement accounts, you want to just, again, do your own research, talk to professionals in the field. So you can do IRAs that are not specifically annuities. There are different types of retirement accounts out there. So I just encourage you to do some research and look at all the different accounts that you could choose. A lot of times when you have an account through your own employer, it may not be, it could be some sort of retirement account. It may not necessarily be an IRA. An annuity, for instance, some can be. So there's just so many different retirement accounts out there. I just want you to be aware that, again, this section here is meant to be really a general overview to give you some basic information. But if you're really looking into investing, you definitely want to talk to a professional before you start investing, or just use your basic knowledge from this class. But hopefully the formulas can give you some idea of how your money can grow. And then you can take that idea, again, and do your research and think about the best retirement investments for you. So let's say you deposit $1,000 into a savings plan at the end of each year for 3 years. The interest rate is 8%, and we're going to compound annually. So we're going to find the value of the annuity after 3 years, and then find the interest. I'm just getting all my numbers out here. Okay. Actually, I'm going to do A over here. I have a little bit more room. All right. So we deposit $1,000 into a savings account at the end of each year for 3 years, and we're going to find the value after 3 years. So notice that we're making the deposit at the end of the year, not the beginning of the year. So that's something to note here. So at the end of year 1, we only have $1,000 in the account, we'll say. Okay, so let's say you've been saving for the first year, you have your $1,000 ready to go. So at the end of year 1, you're just putting that $1,000 in. The end of year 2. All right, so now you have the $1,000 in the account. Now it's actually ready to start earning interest here. So we can use that formula that's listed up top here, that A equals P times 1 plus R to the T, again, because we're just compounding once a year, so it's the simpler formula. I'm starting with $1,000. We're using an interest rate of 8%, so 0.08. And again, we're just doing this for 1 year at a time. So we're taking that $1,000 and we're going to end up multiplying it by 1.08. For the first power, which is just 1.08. And once we do this, let's see, we end up with $1,080. Now be careful here, because your interest from the year before is now an extra $80. So you have that $1,080 in the account. But you're also going to deposit another $1,000, right? Because at the end of every year, you're going to deposit another $1,000 in the account. So the amount from the interest is the 1,080, or the interest in what was already there. But you're also going to add in another 1,000 that you've been saving throughout the year. So you actually have $2,080 in the account at the end of year 2. And we're going to do the same thing again here. So I'm going to start by calculating that interest that's accumulated in the last year. So I'm starting with the $2,080 this time. And again, nothing else has changed here. So it's going to be that same factor of times 1.08. And let's see, and I'm going to get $2,246.40. But don't forget, at the end of every year, you're also adding in an extra $1,000 that you've been saving up. So we're going to end up with $3,246 in. So that's going to be our total in the account at the end of 3 years. Okay, for this specific example. Let's find the interest. Now, it's a little bit trickier here because you have to think about how much have you invested first. So the amount of money that we have actually invested is $1,000 at the end of the first year, plus another $1,000 at the end of the second year, plus another $1,000 at the end of the third year. So we've invested $3,000. So this is kind of like our principal. So your interest is going to be the total that you have minus what you actually invested. So you have made $246.40 in interest in those first 3 years. Now, kind of like we did with compounding, we kind of started off doing the same sort of idea, like let's actually do the calculation manually. We'll calculate once a year and see what happens. We don't want to be doing this calculation constantly, particularly if we're investing in a retirement account where we could be saving for 20, 30, or 40 years. So we have a simpler formula we can use here, and that's this formula here. Now, keep in mind that this formula is only for compounding once a year, so annual compounding. Obviously, we can do it much more frequently than that, so we'll look at some other examples after. But this formula here is specifically when we make a deposit at the end of each year for an annuity that pays an annual interest rate compounded once a year. Okay, so it's very specific here. And again, like I've mentioned, retirement accounts can get much, much more complicated than this. So this example here is when we're doing a one-time investment once a year, and interest is only being computed once a year, and we have a fixed rate as well. So again, this is kind of our simple version, but hopefully you can see how money can grow quickly. That's really kind of the point of this lesson here, is to learn how fast money can grow when it's left into accounts over a long period of time. All right, so let's try this one. Suppose when you're 35, you decide to save for retirement by depositing $1,000 into an IRA at the end of each year for 30 years. If you can count on an annual interest rate of 10% per year compounded annually, how much money will you have from the IRA after 30 years? And we're going to round our answer to the nearest dollar. Again, I'm going to kind of write my A on the right here because I have more room. Now, first of all, notice we're using the correct formula here. So we're compounding annually, meaning once a year, and we're only making a deposit once a year as well at the end of that year. So this is a very specific formula. So we're going to deposit $1,000 at the end of every year. Our rate here is 10%. So 0.1 or 0.10 once we, again, move that decimal point 2 spots left. Our T is 30, so we're going to invest for 30 years. So maybe we're hoping to retire at age 65. And let's see how much we would have. So all I'm doing here is I'm filling in all those values. And just like in the previous videos, I'm really just going to make sure I slow down a little bit because I know I make mistakes too, and take my time here. So first thing I'm going to do is add. So I'm going to have 1.10 to the 30th power. Now I'm going to go ahead and do this calculation out. right, so I have that 1.10. I'm going to raise it to the 30th power. I get quite a large number, or it's not a large number, I should say a lot of decimal places here. So I have that value, and I'm going to subtract it with 1. So I'm just going to do that right together and save some time. Now I'm going to do my multiplication. So I'm going to multiply this by 1,000. And I'm also going to then do my division here. So I'm just going to leave it in my calculator, do a couple steps in one here, and now divide by 0.10. And what I get here, let's see if I can fit it in. I get 164,494.02. We're going to round to the nearest dollar it asks us to do. So this is about $164,494. So that's the answer for part A. Now part B asks us to find the interest. So again, you just need to be careful here. So think about how much money did you actually invest first? Well, we invested $1,000 at the end of every year. And we did that for 30 years. So we did $1,000 times 30 years. So we invested $30,000 of our own money into the account. So your interest then is going to be that total, that 164,494 minus the 30,000, and we get $134,494. So at the end of 30 years, you've accumulated an extra $134,000 in interest, a little more than that, right? That's free money that you did not have. If you had just kind of kept that in your cash in your house, or put it in just to like a regular savings account with like a low rate, maybe a lot of savings accounts now have very, very low interest rates, like 0.5% or something very small. It would not have done this. So this is why long-term investing can be a really good idea. I'm not saying it's foolproof, though. There's a lot of risk that goes into investing, which is, again, why I said this is meant to be an introduction to that. But you should really talk to a professional in the field for advice if you want to start investing. But here, this person made about $134,000 in interest over the course of 30 years with only investing $30,000. Now, we are assuming, of course, 10% return. And it may not, in reality, it may not be 10% every year, right? So historically, the stock market does tend to show an average of 10% for very long-term returns. But if you're going year to year or anything short-term, this can, again, it can be very risky, and also depends when you take your money out. If you need your money and the economy is in a downturn and investments are losing money, then that would be a very bad time to take your money out, right? You're going to lose a lot of money. So again, we're assuming a 10% return here, when in reality, you know, the world is fluid. So your investments could change from year to year. Now we have another formula if you're going to do compounding anything different than 1 year or than yearly. So interest compounded n times per year has a similar but slightly more complicated formula. So you still have P as a deposit made at the end of each compounding period. So if you're compounding monthly, you would make a deposit at the end of the month, right? For an annual interest rate, compounded n times per year, and again, T years here. So again, the thing to notice is that our accounts are compounding and we're depositing at the same rate. So again, these are very specific examples where if we're compounding monthly, we're also making a deposit monthly as well. So they're very in sync. Whereas I said, realistically, most of us are making deposits through our paycheck if we're doing a retirement plan through an employer. Although you don't have to, you could have your own retirement plan as well. But again, hopefully you'll get an idea of how money can grow, which is really the important part here. So at age 25 to save for retirement, you decide to deposit $200 at the end of each month into an IRA. That saves 7.5% compounded monthly. How much will you have at the age of 65? All right, so here's my formula. I always like to rewrite my formulas. I just find it helps me focus a little bit better. And I'm going to fill in my values. So for this example, my P is 200. That's how much we're depositing each month. My rate is 7.5%. And again, in decimal form is 0.075, moving that decimal 2 spots left. Our N is 12 here because we're compounding monthly. Now our T. So we're starting at 25 and we're wanting to retire at 65. So 65 minus 25 is going to be 40 years. So we're investing, we're going to do this for 40 years. And we're assuming a 7.5% return, right? So it's a pretty modest return on our investment. And of course, we're assuming it's the same return every single month. In reality, investment returns do vary, you know, month to month or quarterly to quarterly, et cetera. All right, so let's fill everything in. I have 200. 1 plus 0.075 over 12. The 12 times 40 minus 1. All right, and now it's just calculator work. So I like to go nice and slow here, just so I don't make mistakes. So I'm dividing it by 12, working in the parentheses. I'm going to add the 1 here right away. I'm just going to clean it up like a couple little steps at a time. This becomes 1.00625, and then 12 times 40, 12 times 40 is going to be 400. And then again, in the denominator here, 0.075 divided by 12 is 0.00625. So just cleaning it up a little bit as I go. I'm going to keep working in the parentheses here and do the exponent first. So 1.00625, I'm raising that to the 480th power. You can see I get a number that's close to 20. Now I'm going to finish up in here. I'm also going to subtract the 1. So I end up with 200 times 18.89888859. Okay, I'm using as many decimal places as I can, which is really important when you're doing exponential stuff. Anything with exponents, that's an exponential. So use all the decimal places you can. Now I'm multiplying it by 200. I'm going to divide it by 0.00625. And I get 604,764.4348. All right, let me see. Is there anything? All right, here your book wants us to round to the nearest dollar, so we can do that, I guess. So I'm getting 604,764. Your book got 604,765, if I'm being honest, and it's just because we use different number of decimal places. So if you look at your book, they use less or fewer decimal places than I did in certain parts. They rounded, so that's why we're getting slightly different answers. We're off by about like 0.5 cent, but that's okay. So again, the more decimal places you use, the more accurate you're going to be. So we're looking at $604,000. $604,764, which is awesome. That's a huge amount, right? Right, so over $600,000 to retire on. And let's see how much the interest was. So the first thing I have to figure out is how much have I invested, investments, and your book also calls this total deposits. So let me make sure I use that lingo too. So what we did is we did $200 each month. So in 1 year, it'd be 200 times 12. And then we did this for 40 years. So when you multiply this out, we get $96,000. So we did invest almost $100,000 of our own money over the course of 40 years. But still, what a huge increase. in interest. So when we subtract these two values, we get 508,764 in interest. So by using an investment like this, you end up having over $500,000 in interest going to you for your retirement account. So this is just a great example of why it's important to start as young as you possibly can. If you haven't started yet, that's okay. It's never too late to start saving for retirement. But the youngest you can start, so here this person started at age 25, and they're only doing $200 a month. So that's around $50 a week. It may seem like a lot, but it's not too bad when you think about how much interest you're earning, right? So for $50 a week, you're going to end up with $500,000 in interest. So it really does add up. Now, annuities can be categorized by when payments are made. So the formula used to solve example 3 and really the previous formula as well describes what are called ordinary annuities, where payments are made at the end of each period. The formula assumes the same number of yearly payments and yearly compounding periods. An annuity plan in which payments are made at the beginning of each period is called an annuity due. And this formula is slightly different. So we're not going to worry about that formula here. I'm just kind of, again, making a point that we're doing very specific examples here. And retirement planning can get quite complicated. There's different types of annuities. There's different types of retirement plans that are not called annuities. You can have an IRA that is annuity or not annuity. It gets very confusing with the different retirement options out there. So again, my point here is to hopefully just show you how your investments can grow and to get you thinking about investing in your retirement plan if you haven't yet. Or if you're currently investing, maybe think about investing even more so in it, right? Especially now, a lot of times our life expectancy is growing. So if you want to retire at age 65, then you may still be around for another, hopefully 30 years. So it's a long time to plan for, and you need to really have a lot of money set aside in order to be able to live comfortably off of that in the future. So we can solve the annuity formula as well for P. So kind of like we did before with compound interest, we can rearrange these variables. So using that same formula we started with, you can rearrange it and solve for P instead of solving for A and kind of work backwards. So we can solve the annuity formula for P to determine what we need to invest each period to achieve our future goal. So like how much do I have to invest now to get my goal for the future? So we're going to again assume that the deposit P is made at the end of each compounding period into an annuity that pays annual interest rate, compounded n times per year in order to achieve that certain value after T years. And again, just like before, whenever we're solving for P, you do want to round up so that you don't fall short of your goal. It's better to have a little bit too much than to have a little bit too little, right, when we're saving. Suppose that once you complete your college education and begin working, you would like to save $20,000 over 5 years to use as a down payment for a home. You anticipate making regular end-of-the-month deposits into an annuity that pays 6% compounded monthly. Now, I will clarify here that you do have to be careful. Certain annuities and certain retirement plans may have limits. So for instance, a lot of plans, if they're deemed retirement plans, you cannot withdraw money from them before a certain age or life of the investment or without paying exorbitant fees. So this is an example here where this particular annuity would only be for a short amount of time. So again, you just have to be careful with what you're investing in if there's any penalties for withdrawing your money before a certain period. And a lot of times with retirement accounts, there is. You have to wait till you're a certain age before you can withdraw money. So again, just kind of look more into this if it's something you're interested in. All right, so we want $20,000. We want 5 years. You're going to make regular end of the month payments. So we're doing this monthly and 6% compounded monthly. How much should you deposit each month? So let me go back and find our formula here. I'm just going to rewrite it. And now I'm going to plug in my value. So my A here is 20,000. My R is 6%, so 0.06. My T here is 5, so I'm going to do this for 5 years. And my N is 12 because we're compounding monthly. There we go. Okay, so we have 20,000 times 0.06 over 12, and that's going to be divided by 1 plus 0.06 over 12. Let's see, N is 12, T is 5, minus 1. So we're just going to go ahead and, again, just start cleaning this up. So that 0.06 divided by 12 is 0.005. So I have that done first. I'm going to multiply that by my 20,000. So my numerator is going to simplify to 100. And in my denominator, again, this is 0.005, so I have 1.005, and then that's going to be to the 60th power. So I'm going to go ahead and do that computation next, right? I'm going to subtract it with 1, and I get 0.3488501,525. So finally, I'm going to go ahead and divide. So 100 divided by 0.3488501,525, and I get about $286.66, I guess. All right, now this one wants us to round up to the nearest dollar, so this is going to be about $287 per month if we round up to the nearest dollar instead. So let me just push this down so you guys can see all that work there. Excuse me. So we're going to deposit about $287 a month, and we're going to do this for 5 years. Now, Part B asks us how much of the $20,000 down payment comes from deposits and how much comes from interest. So again, we're trying to find the interest here, which means I need to figure out how much I've invested myself. So the amount invested, also called the total deposits. Well, we're going to do $287 every month, so times 12 months in a year, times 5 years. And let me see, I already have this done. And that becomes $17,220. So the interest here is going to be the 20,000, right? Because that's our end value, minus the 17,220, and we get $2,780. So when saving for the house, we have $2,780 in interest, and $17,220 is in our own deposits. Now, we didn't earn too much interest here. I mean, it's still almost $3,000. It's a lot of money, but because it's only for a short period of time. So when you earn a lot of money is really when you're doing this for an extended period of time. So even 5 years is not that long. Our last examples were like 40 years, 30 years. So that's when you really start to grow that money.